impact on virtual power plants on power system short-term transient response. It will be presented by Weilin Zhong. Mr. Zhong?
Yes, I'm here.
Okay. Would you like to make your presentation?
Yes, of course, sir. Thank you.
Okay. Thank you very much.
Thank you. Let's see. Good afternoon, everyone. I will give the presentation about the impact of virtual power plants on power system short-term transient behavior. At first, I think let's define what is virtual power plant. In our paper, the virtual power plant is considered as the aggregation of distributed energy source installed in a distribution grid, including distributed generator, dispatchable loads, as well as the energy storage systems. Nowadays, the most studies on virtual power plants are focused on the operation and economic aspects to minimize the performance of its device. For example, the distributed generators, dispatchable loads, and ESS by correlating the production and consumption. The transient behavior of the virtual power plants as well as their impact on the overall power system dynamic response are not thoroughly studied. And moreover, it seems the coordination of distributed energy source requires the exchange of measurements and control signal among controller in a centralized structure VPP. The communication delays are introduced. So the purpose of this paper are twofold. First, a centralized coordinated frequency control structure for DERs is included in a VPP, and the impact of such architecture on the overall transient behavior is studied. Then it presents an in-depth analysis of the impact of delays on the overall dynamic response. Here is the centralized control scheme of the VPP. The frequency is measured through a PMU at the point of the VPP coupled with the transmission grid. All distributed energy sources use the same frequency signal as an input signal in their local control loop. Then the information of each DER is sent and collected by a data management system located within the VPP. Note that during the data transmitted from PMU to DERs or from DERs to DMS, the communication delay related to the measurement and dispatch of the data should be considered. In our paper, we are using ESS to support the primary frequency regulation. There are two loops in our ESS control scheme. The inner loop is used to eliminate the deviation of the measured frequency and the reference frequency. The outside loop is used to introduce the power generated by the VPP, where PCO is the feedback signal. PESS local is the active power output from the local ESS. PNet is the net active power of the VPP. PESS, PWind, and PSolar are the sum output of the active power from DERs in VPP. And the P-reference is the inertial reference set point equal to the PNet. Finally, P-loss, P-load, and P-inject are the total active power losses and load in VPP and the injection from the VPP to the transmission grid. There must exist communication delay in the centralized control structure. So the remote active power signal from the VPP, here is the PNet, is delayed in our model. Here the delay, where the delay tau t can be considered as a wide area communication delay and considered as three parts, where tau f is the fixed delay associated with sensor use and data processing. Tau p is the transmission delay, and theta is the random jitter. We consider the simulation be more realistic, we also introduced the stochastic process in our simulation. Here is the stochastic model, and here is the stochastic wind model used to inject to the wind turbine. And here is the stochastic voltage-dependent load model. Let's move on to the case study. Our test system is a modified version of the WSCC 9-bus system, where the load at bus 6 has been replaced with a VPP. The VPP is connected with the transmission system through a UTLC transformer. The inertial active power generation. The inertial active power generation of the wind power plant and the solar PV plants are 15 megawatt each. For all the scenarios, the contingency considered is a 3-phase fault at bus 7 and cleared by opening the 9 connecting buses 5 and bus 7. The result is the frequency response following the disturbance for the four scenarios. The first one is with ESS and without DER control, frequency control. The second one is with DER's frequency control and without ESS. The third one is with non-coordinated DERs and ESS. And the last one is with coordinated ESS and DERs. If the ESS is installed in the VPP, the steady-state frequency error is lower compared to the case without the ESS. However, it's still not zero due to the limited capacity of the ESS and the fact that the AGC is not considered in this simulation. On the other hand, the frequency shows the maximum deviation of the case where the DERs do not participate to the frequency control. The best dynamic response is achieved through a coordinated control of DERs and ESS, which is proposed in this paper. And the reason is that by adding an outside loop in the ESS control, the coordination of the DER's output can make the ESS reach its maximum power output limit after the contingency. The communication delays of the remote signal transmitted are taken into account in this section. 3 levels of communication network, named high speed, middle speed, and low speed, are considered. All the remote signal are considered as PMU data, transmitting through a point-to-point communication link, and the packet size of PMU is 100 bytes. The reporting rate is 25 frames per second. The communication protocol is UDP-IP to avoid the data retransmission and reduce the communication delay. Background traffic, for example, the remote terminal unit data and video streams, are also considered. Here is the arrows of the frequency at bus 6. The signals are transmitted through a different level communication network and compared with the non-delayed signal. The high-speed communication network has a better response compared to the other two. The signal transmitted through a low-speed network has a more significant delay, which leads to a larger frequency deviation, even if the background traffic in such a network is ignored. Observe that the impact of communication network in frequency response is nonlinear. The frequency deviation between the high-speed and middle-speed network is smaller than the deviation between the middle-speed and low-speed network, which means there exists a critical range of the bandwidth, over which increase the bandwidth can only slightly reduce communication delay. It is expected to find a suitable bandwidth of the communication network that the impact of delay on the system response is acceptable, and the cost of establishing such a communication network is economical. The impact of stochastic process is also considered. In this section, we consider stochastic variation of the wind speed and 10% of the loads in the VPP. 500 Monte Carlo simulations are carried out for each of the 4 scenarios considered in this case. Comparing the standard deviation of frequency at bus 6, the VPP without frequency control on DER shows a worse performance, where other 3 control schemes do not have significant difference. However, the coordinated ESS control scheme managed to recover the frequency closer to the reference value. So, this paper studies the impact of virtual power plants on power system structure dynamic response. Contingencies and stochastic variations of the wind and voltage-dependent loads are also considered. Simulation results indicate that the BPPs with coordinated the control of ESS and DER shows a better frequency response compared to the cases without coordinated control. Simulation also indicate that the delays of different communication networks on the transient response have a small impact, which suggests that the coordinated control is feasible and its technology does not necessarily impact on the dynamic performance of the VPP. That's all. Thank you.
Okay, thank you very much for your very nice presentation. We don't have any question from the chat. Well, I have one question.
Okay.
I think that there is a very interesting topic that it's, you know, the problem of controlling or improving the dynamic performance of the system at the transmission level. Imagine power oscillations, mechanical oscillations between the synchronous generators, but using elements from the VPP, distributed elements, or at the distribution level. So the point is that probably these elements should be controlled, measuring variables at the point of connection, but having delays because of the communication, because of the fact that the input signal is a remote one, it is not local.
Yeah.
Have you investigated, do you plan to investigate this in your I think that you're a doctoral student, is that correct?
Yeah.
Okay. Do you plan to address those issues?
You means the delay, if you have some difference delay in the centralized control structure, right?
Yeah, imagine that, you know, we are used to, you know, just to a synchronous generator controls its terminal voltage.
Yes.
However, if we want to control, to damp the oscillations in the transmission system, you need to measure what is the voltage or the frequency, bus voltage, bus frequency in the transmission system. But then the control action is through a number of distributed elements. And there is a delay between the measurement at the point of connection and the action in the distributed element.
Yes, I have already considered this. You see that I consider 3.
Okay.
Yes. So every device like here, like the PV, the ESS, and the wind turbine, I have already used different delay.
Oh, very interesting.
Yes, it's
Okay,
easy
very,
because
very interesting.
I have implement cool simulation software.
Oh,
Like yes, in NS3 is a network simulator. I can set up my communication network topology and generate the different delays based on my parameters.
okay, okay. Thank you very, very much. Very, very interesting. Okay, I think that we have one question in the here. How
Uh,
do you consider the parameter sensitivity of the simulation results?
Parameter sensitivity.
Yeah, the audience has not specified which parameter.
Hmm, I'm not sure what this means. How
Yeah,
do you,
okay.
yeah,
Neither
parameter.
neither I do. Okay, okay. Yeah, we have a new question, a clarification. If you change some parameters, maybe the results will change a lot.
You mean the parameter of the controller?
Yeah, probably. Yeah.
Yes, yes, it will change. So this result is the yes, yes. The result we have through a lot simulation, and the result is in every case is the best result.
Okay.
Yeah.
Okay. Thank you. Thank
Yeah,
you.
thank you.
Do we have any other question? No. So we are in very good time. I think that we still have 10 minutes if there are any missed question. No. So I only have to say thank you for all presenters for very interesting presentations. All of them have been very much on time, and we have had a very lively discussions with many questions from the audience. For your record, we started being 27 people, and at the peak we were 60 people connected. Now we are 44. Okay, we thank you all for your participation and hope to see you soon in presence. Okay, I think that Federico